probably just share the screen maybe.
Okay. Okay, just a brief introduction to Professor Divya. And Dr. Divya Padmanabhan is an assistant professor at School of Mathematics and Computer Science at IIT Goa, and she is our alumni. Thanks to dissertation with admission. It's nice to have our alumni to give our first talk in this workshop, right? And she was recently at UST pillar of Singapore University of Technology and Design, and then she received PhD from the Institute of Science, and basically her research interests are broadly lies in focused optimization and decision making under adversariality, and also she's very like a trained Carnatic musician. I think she's participated in All India Radio and video too.
Yeah. So hello everyone. I hope I'm audible.
Yes, yeah.
Yeah, and I hope the slides are visible too. Right?
Yes, yes.
Yeah. Okay. So first of all, thank you so much for inviting me to this workshop. It's a real pleasure to be presenting here. And of course, IISc is, I'm an alumni from IISc, so it's an added bonus. So today, what I'll be talking of is this work that we did recently. It's titled Correlation Robust Influence Maximization. So this is based on joint work with Louis Chen, who is an assistant professor at the Naval Postgraduate School at Montreal. Chi Chen, who is a doctoral student currently at NUS Singapore, and Karthik Natarajan, who's a professor at SUTD Singapore. So this work, we started this about 2 years back, and that was a time when all of us were in Singapore. So I was a postdoc at SUTD with Karthik Natarajan, who was my advisor, and Louis had come down to visit for about 3 months. And Chi Chen was an undergrad student at SUTD at that point of time. So that's when we started, and then gradually we developed this whole work. And so I have to say that this work, the contribution is primarily in the area of distributionally robust optimization. It uses techniques from robust optimization. So some of these techniques might be kind of new for this audience. So what I will do is, as I get into the specifics, like when I get into the relevant part of the talk, I will give some more insights on these techniques. Okay. So let me get started. Yeah, so as the title suggests, it's a contribution in the area of influence maximization. So I think influence maximization is a problem that probably this audience is very familiar with, because it's a, it's a well-studied problem in computer science. But just for completeness, if there are people who haven't seen it, I'll just introduce the problem. So what you want to do typically in an influence maximization setup is to maybe disseminate some kind of news. Maybe you are a CEO of a company and you want to have at your hand is a social network. So social networks are there everywhere today. So things like Facebook, Twitter, and so on. So the network, you can make use of the services offered by the network to spread the information that you want. Okay, so how do you do that? Instead of contacting everybody to all the users in the web, what you do is you contact a few people. You choose a few people from the network, and these are the sort of influencers, and they help you to spread the information in the network. Okay, so that's the problem here. And the question is about which are the influencers that you want to select. Okay, and so more formally, the underlying network is modeled as a graph with a set of vertices and a set of edges. And the problem is to choose the set of influencers. So this is called a seed set in this terminology. So the seed set is S. And the seed set is limited by the number of nodes it contains. So there's a limit of this number K. So this is primarily based on things like budget constraints, because for each influencer you hire, you have to spend some amount typically. So you are restricted by your budget, and that's why there are just k nodes. So you want to choose the seed set so as to be able to influence a maximum possible number of nodes in your vertex set. So that's the problem. And one thing that is in the network, but it's not known to you, is the influence activity. So each of these nodes represent people in the network, and the edges represent the connections. So the, who, like the friend network, for instance. Okay. But the exact which influences the other, that is not known. They may be connected, but you never know how well the influence relationship holds. Okay, so that is random, and that's what is referred to as Cij. It's a random quantity. And it's a Bernoulli random variable. More specifically, it's either 0 or 1. So all that you know is that the probability that Cij is 1, and that is a value equal to Pij. Okay, and so this is the random model that's assumed. And there are a lot of works, a lot of models to deal with influence maximization. And one of the most well studied ones is this model called the independent cascade model, where all these random variables, the Cijs, are assumed to be distributed via independence. So the joint distribution is through independence. Okay. So there are so many other models there. Unfortunately, I'm not going to be able to go into the other models. I picked the independent cascade model as this is the closest one to what we develop. Okay. So yeah, so this is the framework. And formally, we represent R of CS as a number of nodes that you can reach with a seed set S under a particular realization C, a given realization C. And given this distribution of the C's, what you're interested in is the expected value under theta IC, which is the independent distribution. And what is the seed set that maximizes this expected reachability? Okay, so that's the problem being solved by the independent cascade model. Now, unfortunately, this problem is NP hard. And even for a fixed seed set, computing this value, this expected value, that itself is known to be hard. Okay, so this is the seminal work of Kemp, where they discuss the independent cascade model and the hardness results. So yeah, what do we do then? Okay, so this is hard, and subsequently there have been like a lot of works where people have tried to propose approximations. I mean, even in fact, in this work by Kemp, there's an approximation, but people have tried to build faster approximations and so on. Okay, so now coming to what we do in this work. We question this assumption of independence. If you think of it, why did we make the assumption of independence? Is it that, I mean, we already saw that it does not help in the computational aspect. It makes, I mean, the problem is quite hard with independence. So one possible reason was that, okay, this was a natural model to assume, right? Like you just assume that all behaviors are independent. But actually, if you think closely about the problem, the influence maximization, uh, it's these influencers who have to spread information about some news or about some product. Now, there is this personal component also that comes in many a time. So if there is some news that somebody has to spread, if this influencer, if they identify more with what they have to spread, then they are probably more aggressive in spreading this information. For example, I am very interested in music. So if there is some new information that comes up on music or a new product, I identify more with it, and I would want more people to know about it, right? So in that sense, the set of people whom I influence, my behavior and influencing my contacts, that will be tied together in some ways. There's some possible correlations that could arise between these edge activations. Okay. And this is also something that you see everywhere, even in the case of politics, like the news associated with politics. People feel very strongly about some particular party and so on. right? So the independent assumption may not be always the, it may not hold in practice always. So what we do is we only assume the marginal distributions, the Pij values, and we don't make any assumptions about the joint distribution. Okay. And so what does that mean? So what we assume is only this value Pij, right? And now we have a family of joint distributions rather than a single joint distribution. So there's a family of distributions all consistent with these marginals, Pijs. And so these are just constraints which enforce that, these are consistent with the marginals and it has to be a valid distribution. So C is the random quantity and the number of realizations is as much as 2 power n, where n is the number of edges. So that's why every distribution is a vector of size 2 power e or 2 power n. Okay, so that's what this set is. And what we typically are interested in this model is the worst case reachability. We have a set, we have a family of distributions. Now from this family, which is the distribution, or what is the worst possible expected value that you can get for the reachability for a given seed set. That is the min value of this expectation over all the distributions in this family. And can you do something to improve the worst case reachability? So what is a seed set which maximizes the worst case reachability? So that is a distributionally robust seed set. So you can see that there is a two-stage problem here. There's a max problem and there is a min problem as well, right? So what I will refer to throughout this talk is the second stage problem will refer to this the min problem, the min expectation. And the first stage is the max problem. Okay, so F core the core denotes that it's a robust model, robust to all possible correlations that can arise in the joint distribution. Okay, so at this point, I would just like to ask if there are any questions before I proceed further, because the model is slightly of a different form. So, Professor Ambedkar, are there any questions so far?
Yeah. So far, nothing. If anything is there, I'll ask.
Sure, thanks. All right. So just a second, I think I just want to check. I think. Okay. So am I audible?
Yes. Yeah. You
Okay.
can see your screen also.
Okay. Okay. So so I just wanted to check this. Yeah. Okay. So the robust model is a two-stage model, a max min kind of a framework. And so what I will do is I will spend some time to discuss the second stage problem, which is this one. And also after that, I'll move to the first stage problem, which is the overall problem. And before doing that, I just want to spend some time on this function, this R of CS, if you knew everything, if there was no randomness in the model. Okay. So what this means is that, I have this graph here. Now, all these Cij values are known to me. So that is given in bold. And I have the seed set S. Suppose I'm fixing the seed set S. And I want to find out what is the number of nodes that I can reach from S. So for this network, I can reach the node 5. I can reach the node 7. I can reach the node 6 through 2 because there's a connection from 2 to 4 and 4 to 6. And then I can reach the node 7. Okay, finally. But the node 4, I cannot reach immediately. Or maybe I should just say it as, there are just 2 nodes which I can reach because 7 is at next point. Okay, so how do I compute this value? How do I get the total number of nodes that are reachable from S? Okay, so it turns out that here is where there's a max flow problem that helps out. So what I could do is instead I could add these auxiliary nodes S and T, and I add these intermediate connections from S to every node in the seed set and from every other node to T. Okay, and then what I do is I can just solve a max flow problem. So what's the maximum flow from S to T? I can just solve that. assuming that the capacities of each of these arcs is 1 or Cij, depending on whether Cij is on or off. Okay, and turns out that that gives you the number of nodes that you can reach from a seed set. Okay, so that is this value Z of Cs. Okay, so the deterministic problem, if there was no randomness in the, the way people influence each other, you can compute the number of nodes reachable efficiently via a linear program. And also max flow, min cut, those are like standard problems with various other algorithms as well. Okay, but the important point I want to kind of draw here is that it's solvable via a linear program, and in fact all the extreme points are 0, 1. So that helps us further when we go into the robust model. Okay, so why does it help us? So that brings me to this result. If you have an integer program, right, and an efficiently solvable integer program over the 0, 1 polytope. So this point is an important point. So if you have an optimization problem, a linear optimization problem over a 0, 1 polytope, where there's some randomness in the objective, then it turns out that the maximum expectation, the maximum value of the expectation for the same class under the family of marginal distributions, that is efficiently computable, provided z of c is efficiently computable. If the deterministic problem is easy to solve, the max over expectations is also easy to solve, and this is the formulation that helps to do that. Okay, so this is comes up in it's a very old result actually, and so this is the case when the optimization problem is in the max form, and you have a max of expectations. Okay, in our case, what happens is we have a min over min expected value, and the z of c is a max flow problem. But the uncertainties lies in the objective here. The Cij's, come up in the constraints. So by taking the dual, what we are going to get is the problem in this form. Okay, and so the analogous results hold here. So if z of c is a minimization problem, and then in that case, the min expected value is efficiently computable if z of c, the original deterministic problem, is efficiently computable. Okay, so this formulation actually helps us to propose more efficiently solvable results. And so based on this, what we get is, if we plug in this formulation, what we get is another linear program. So the worst case expected value can be computed using this formulation here. And this is actually a linear program. So remember that the worst case expectation is computed for a given seed set. And so S is known here at this point because it's a second stage problem. And the linear program, if you look at it, it's a very efficiently computable program. It grows just as big as a network. So it's about V variables and order of V plus E constraints. So the variables are these pi i's, and the constraints, there are as many as, it's order of V plus E. Okay, so in that sense, it's efficient. So one thing I want to also mention here is that these pi I variables, they have some nice interpretations. So in particular, we can show that these pi i's, they can be interpreted as the probability that you can reach a node I from S in the worst case. Okay, and so one thing to highlight here is that remember that in the independent cascade model, where the joint distribution was specified via independence, the expected value could not have been computed in polynomial time. Whereas here, for the worst case expectations, if you don't impose a joint, the worst case expectation is computable in polynomial time. So via this linear program, so it's a polynomial time solvable problem. Okay, and one additional point I also want to add is you can do something even smarter than solving the LP. So the LP itself has an interpretation as it's a shortest path problem. So you can use the standard of methods. Okay, so the reason that happens is because of this constraint. So if you try to simplify the constraint a little further, what you get is the pi I stars. It actually boils down to evaluating a number over all paths. So each path you take, each path from S to I you take, and there is a value associated with that path, and that depends on each of the edges. So it's as if each edge has a weight of 1 minus Pij, and there is this kind of a metric, and you try to compute the max value. So it actually boils down to a shortest path for a graph of this form. So you can compute pi I stars using just shortest path calculations. And in fact, we do this in our experimental results as well. Yeah, so that's about the about the second stage problem. Now, what we want ultimately is the seed set. So what we saw so far is, given a seed set, what is the worst reachability? What's the worst expected reachability? Now, can we find the best seed set? Right? That's the original problem we started with. So here, what we do is, the part that I've given in blue, that is just the second stage problem that I showed. So the seed set S, you can represent it using some binary vectors, where each element x xi is 1 if I belongs to S. Okay, and so you can plug this into the formulation. So pi I is greater than 1 for every I in the seed set. Okay, so that's why you have this constraint. And so you have these additional constraints, that is for for imposing the cardinality of the set. So this could be less than or equal to ideally, but of course, if you have a budget of k, you wouldn't want to choose lesser. You would choose exactly k nodes. Okay, and another thing is that these are all 0, 1 constraints for the x's. Now you can use the standard dual trick. You can take the dual of this problem, which is given in blue, and what you get is this maximization problem. Okay, and so what I've written here is just the dual part, and of course there is z, w, and y other variables. And finally, for the first stage, you will solve a joint maximization problem, and x also becomes a variable. But the issue here now is that we have lost the linear programming part, the linear programming advantage. And we've got this kind of a quadratic term because x and y are both variables. And also an additional complication is the 0, 1 constraint. So these are two issues with the first stage problem. Okay, so how do we go about? Right? And so the part about these quadratic terms, there's something we can do there. So what we do is we just do a linearization. So wherever x, I, y terms come, you just replace it with another variable. And it turns out that you can compute these kind of upper and lower bounds for these xi and yi's. So of course xi is 0, 1, so it has to be between. A lower bound is 0 and an upper bound is 1. Okay, and as far as yi's are concerned, we can show from the constraints that it's bounded below by 0 and it's bounded above by the number of vertices. Okay, now if we have these kind of lower and upper bounds for these variables, there are these sort of McCormick inequalities which you can plug in. So the McCormick inequalities are shown in blue here. So instead of, you of course, you replace every occurrence of xi, yi with this new variable and include these kind of constraints. And it's not always guaranteed to be exact. But in this case, since every occurrence of these linearizations, it's separable. So you don't have things like xi, yj terms. And such things are not showing up here. And so we can show that these are right. These inequalities are sufficient to capture the exact value of the previous problem that I showed. Okay, so we've taken care of the quadratic terms. Now, only thing that remains is the 0, 1 constraint. So at this point, what we can for sure tell you is that there is an exact MILP, an exact mixed integer linear program to compute the best seed set, the robust seed set. Okay. So this is something which is not possible for the independent cascade model, because even computing expectations is itself hard. So, you cannot find you cannot optimize for the seed set there using an MILP to the best of our knowledge so far. And can we do better than this? This is an MILP, so it works well for smaller problems. But the issue is that there is still an inherent hardness in computing the optimal seed set. So this is still an NP hard problem. And we show this in the paper. The proof actually follows, it's a very simple adaptation of the hardness of the independent cascade model. Okay, so it's actually, it's a reduction from the set cover problem itself. So what this implies is we could use MILPs for smaller size problems, but what do we do for larger problems? Because typically in social networks, you have like large networks. So maybe MILPs is not the way to go. Right? So that brings me to the next part of this talk, which is on approximations. So how can we get good approximations? Right? And yeah, so one thing is in the independent cascade model, there's some feature which helps, which is mainly the submodularity of the reachability function. So just for those who are not familiar with submodularity, what it means is that if you have a set S and if you have a larger set T, okay, and you're trying to bring in a new element X, okay, and there's a function, which you are using to evaluate the goodness of these sets. So bringing X to S, that gives you a greater contribution than bringing X into T, right? So it's sort of like the diminishing returns concept. So if you include an element into a smaller set, the benefits you get are more. Okay, so that's what is mathematically stated in this inequality. So it's just that here we have this. There is a random variable also. Now, if you fix the C's, if you fix the configurations, we can show that the reachability function is submodular in the S. Okay, and so this is shown in the original paper by Kemp, and so one thing is that, now if you take the expectation over any fixed distribution, the submodularity is retained. But one complication is that, for the robust model, we are working with this objective, which is a min over expectations. And that is not guaranteed to be submodular. Okay, so in general, you don't have this property. But what we show is that in the case of influence maximization, it's something very specific to this objective, uh, the reachability objective. Uh, for this problem, even the worst expectations, the min over, this family of distributions, that is also monotone and submodular. Okay, so the reason why this is not necessarily submodular in general is because you take one seed set S, then there is maybe some distribution which is a worst case distribution. Now, if you change the seed set, it's a different distribution that comes into picture. So then you cannot guarantee that this kind of an expression holds true. Okay, but in this case of influence maximization, somehow we are able to show that it's indeed submodular, monotone submodular, and in fact the proof of this makes use of this particular values of biased the closed form expression that I showed you earlier for the worst case reachability of each node. Okay? Now, a consequence of a monotone submodular function, we can use this greedy algorithm. So what you do is you start off with an empty set and you try to measure, for each of the nodes, you try to measure this worst case expected value and you try to choose the one which gives you the best. Now you try to go into a seed set of size 2 and you keep doing this till you hit k-bits. Okay? So that's the greedy algorithm. And for monotone submodular functions, there is this 1 minus 1 by E approximation guarantee due to Nemoser, Wolsey, and Fisher. Okay, so that we make use of these guarantees here for the robust model. Okay. So just a quick recap. So what we have done so far is I've talked to you about two models, the independent cascade and robust model. In the independent cascade model, the function to optimize was an expected value. And in the robust, it's a worst case expected value. And the computation of the function is NP hard and independent cascade, whereas in the robust model, it's easy. And but the solving optimization for both is NP hard. And submodularity is retained for both. And for the robust model, we have this 1 minus 1 by E guarantee. In the independent cascade, there is an additional minus epsilon factor which comes in. That's because once you're trying to evaluate every seed set, you're trying to compute this function, and that cannot be computed efficiently. So you have to do some kind of sampling. And because of that, there is this factor of minus epsilon which comes in. Okay? So this is about these two models. So what we did is the robust model, and I showed you how we do the computation. Now I'm going to spend some time on looking at these seed sets. How do you analyze the seed sets? Computationally, we know that the robust model is good, but what does it offer in terms of the seed sets obtained? Okay. So to analyze this more formally, what we did is we had this kind of a metric, the price of correlations. So our interest here was, since we have a robust model, we wanted to see how does the independent cascade model perform when you have an adversary. Because the robust model is actually trying to do something in the face of an adversary. Possible correlations that are going to happen. So in that sense, it's an adversarial diffusion process. So what we wanted to see is how does the IC model perform under such a process. So to do that, we use this metric, the price of correlation metric. So what it says is that in the numerator, we have this SIC, that is the best seed set for the independent cascade model. How does it perform under an adversary? I mean, the F core of SIC. So with the worst expectations, how does it perform? And in the denominator, we have the robust seed set. So the max value, the best you could do is when you use the seed set from our model. And what is this ratio? How different can it be? So of course, this value is always less than 1. Okay, because the denominator is always, it's the optimum, it's the best you can do there, and so it's less than 1. Now, actually, you can show that it's greater than 0 also, but there's also another lower bound that you can produce here. So it's just this ratio of how the SIC performs under a worst case versus how it performs under the independent cascade, which it was originally designed for. Okay, so these inequalities are, it's just the consequence of the correlation function being a worst case, being a worst case computation. Okay, so what does this mean? So if we have a price of correlation close to 1, it means that the independent cascade model is not performing very badly. It's still performing reasonably well when there's an adversary. But if it's close to 0, its performance is very much affected by the adversary. Okay, so we try to compute or get some results on the values of the price of correlation. Now, the price of correlation metric is something that has been used in the literature in robust optimization. So there's this paper by Shipra Agarwal where this quantity was introduced. So there was some difference, like we adapted this to the case of worst case expectations in the sense of minimum. So the minimum expected value where a Shipra's paper was designed for the case of max expectations. Okay. So now, just to see some examples of this metric. So if you look at this kind of a chain graph with n nodes, and the probabilities of activation is 1 minus 1 by n for each of these edges. In that case, we are able to compute the correlation gap, which is a lower bound for the price of correlations. And so the price of correlations is at least 0.791. So what it means is that the independent cascade model performs at least like 80% of what the worst case model does, of what the robust model does. So it's not very bad for this example. But actually, we are able to construct some examples where the independent cascade model is hurt very badly in the presence of an adversary. So that graph is something of this form. It's like a huge tree where there's some randomness in the initial part, and yeah, so as this graph explodes, the price of correlations tends to go towards zero. So this is the case where these kind of graphs are affected a lot by the adversary. So this is just to show that the robust model is adding value in some of these examples. So okay, so far what we saw was the expectation objective. We tried to find the seed set to maximize the worst case expected reachability. Now, what I'm going to do is I'm going to show some extensions in the context of risk aversion. So whatever I covered so far was, you can find these results in our paper which appeared in Europe's last year. And subsequently, we worked on an extension. So I would like to spend some time on that. So Professor Ambedkar, how much time do I have?
So you still can have like 10 to 15 minutes.
Okay, okay, perfect. Okay, so yeah, so okay, so expectation is something that yeah, people understand very well. Now, I just want to tell something about this concept of risk aversion, where we use these kind of metrics like conditional value at risk and value at risk. So these are metrics which are pretty much well studied in finance and insurance, those kind of domains. So just to get some sense about it. Okay. So consider the a very simple problem where you are trying to estimate the income of people in a country. Okay. Uh, so what you can do is you can compute the average. You can generate some samples and compute the average income, and you can think that that is a representative of the income. Now, if there are a few rich people in the country, what's going to happen is that they'll pull the expectation up. Okay, so in that sense, it's not a very fair. It doesn't give a very fair picture about the the entire population. You could use the median, so that would give you maybe a better sense of how how the income is distributed. Or if you are interested in the poverty line, like if you are interested in the poorest people of the country, what is the average income from them, right? So that gives you a sense of the bad region in some sense, the bad population, and how bad are they. Okay, so the conditional value at risk is just trying to capture the notion of these bad regions for any random variable. So more formally, suppose you have a distribution, you have a random variable x, and you have its distribution. It's a fixed distribution. Let's assume that. Then there are these two tails. Okay, so the tails of this distribution tell you, one of them is a good part and one of them is a bad part. So, so let's take, I mean, for the influence maximization problem, it's the random quantity is the reachability metric, and a large value is what we desire. So smaller values are the bad regions. And suppose this region, right? So that has the tail, and suppose that has an area of alpha. So that's the probability of the bad region. Suppose we are interested in the alpha probability regions. Then what is the point at which you achieve this alpha probability? So that is the value at risk. So this point here, the value of x for which you get this probability, that is the value at risk. And the conditional value at risk is the expected value corresponding to the shaded region. Okay, so that is the expected value of the bad region of this random variable. Okay, so this is it's going to tell you a sense of how, I mean, it's a measure of risk in some sense, because it's quantifying the bad region. Now, it turns out that the CVAR, the conditional value at risk, can be computed using this convex optimization problem. So this is for a fixed distribution. Okay, so there is an expectation here. So that is for the particular distribution that you're trying to measure this. And you can see more about this in these results by Rockefeller and Uriasel. So what we do in this work now, this extension, is to see how bad can this CVAR be. Okay, so for each distribution, there is a bad region. Now we have a family of distributions. how bad can the bad region be out of these various distributions, out of these various consistent distributions. So that is the worst case conditional value at risk. Now, what we seek to find is a distributionally robust seed set, which optimizes the worst case CBAR. So what is the seed set which improves the bad region out of the bad distributions, out of the worst distribution? So that is what is this problem. So you can see that it's almost very similar to what we saw earlier. It's just that the metric here is the CBAR metric, which is the expected value of the left trail region corresponding to each level alpha. So alpha is an input. Okay. So it turns out that whatever techniques we have here, that also extends to the case of CBAR. So the second stage problem, so this is the second stage problem now, and that can be computed efficiently uh, using this sort of a linear program. Okay. Uh, right. So, and now the next thing is about the first stage problem. Can that be computed efficiently as well? And of course, the answer is no, because setting an alpha equal to 1 here, that would correspond to the expectation for it boils down to the original expectation case we saw. So the problem is, it remains hard. But here what we see is that, again, there's this notion of submodularity, which we try to check here. Now, an interesting point here is that for the independent cascade model, the original expectation value, that is a submodular function, as we saw. But somehow when you go to CBAR for, because it's a more general concept, because you can have different values of alpha here. So of course, if you keep alpha equal to 1, it's the CBAR for the independent cascade, that's also going to be submodular. But there is this example here we have for this graph. This is from this paper by Mehara, where they've also studied the CBAR objective in influence maximization. So here what happens is that, if you take this set, this node 4, and if you're trying to bring it to the set 3, right? If you're trying to include it there, the difference that you have, the improvement is this value, this 1 for the independent cascade. Now, when you're trying to include it within, if you're trying to add it to the set 2, 3, the difference you have is 1.5. Okay, so CBAR metric for this alpha, it's not submodular. Okay, because a larger set is giving you, adding this element to a larger set is giving you more benefits. Okay, but whereas the worst case CBAR, in this case, actually it turns out to be, it doesn't break the submodularity inequality. So actually what we show in the paper more generally is that the worst case CBAR actually retains submodularity. Okay, whereas the independent cascade CBAR does not satisfy submodularity. This again has to do with the particular form of the worst case distributions and the separable nature of the computation. And also there's some kind of an ordering of these nodes of the graph, and that's what helps in the worst case. Okay, whereas that kind of an ordering is not something that we see in the independent cascade model. Of course, I'm brushing some details aside because, I think it's for want of time. Right, so just to again summarize these, the first set of results here, that was to do with the expectation, the vanilla expectation case. And the next set of results here has to do with the CBAR, the worst case CBAR and the CBAR for the independent cascade model. The key difference across these tables is on this point of the submodularity. Okay, so if you look at the submodularity part, for the independent cascade model, under expectations, it still retains submodularity, but under CBAR, the submodularity is not retained here. And whereas for the worst case, the submodularity is still retained when you go for CBAR worst case. And so that allows us to use, again, this 1 minus 1 by approximation guarantee for the greedy algorithm. So this result is there. Now, this work by Osaka and Yoshida also look at the independent cascade model under the CBAR objective. And there they are able to propose an approximation. So to get this seed set, the best seed set there. The only difference is that it's not a deterministic seed set they get. It's sort of they need to do some kind of a randomization to get a portfolio of sets. Okay. So this is a contrast between the two cases. So somehow, just as a takeaway from these techniques, these worst case models at times they seem to help computationally, and they seem to simplify the problem more than the stochastic case. So that I would like to emphasize on that takeaway here. Now, just some insights from our experiments. So I think I'll probably take about 3-4 minutes to talk of this. So these experiments were performed by Chichen, who was an undergrad student at SUTD, and I think he did a really wonderful job with these experiments. So there were these two data sets, this Wikivote and PollBlog's data sets. So the details are given here, and what we did is, of course, we cannot compute the exact optimal seed set for all these models because there's some hardness. But what we compared is the greedy solutions to these models. So S score G represents the greedy solution to the robust model, and SICG is the greedy solution under independent cascade. So there you need to do some kind of sampling to evaluate the expectations, and we use the accelerated greedy algorithm to speed up these computations. And our code is actually available on this link, so please feel free to use it for any comparisons, or if it helps you. So the first thing is a comparison of execution times. So if you look at the graph on the left, so if you see the PollBlog's data, so that is blue and yellow, so these two. So the blue one is the robust model, and the yellow one is the independent cascade, and of course the blue one is faster. And similarly here you see it for the other data set, the green, this one is for the robust model. Okay. So this is something which also reflects for different values of P, and we've checked this, that the robust model is indeed faster. And on the seed set analysis, so we were trying to mimic some of the concepts and price of correlations here, but we don't have the truly optimal seed set for any of these models. So what we did was, we computed this sort of misspecification ratio. So what it means is that S score G, this is the seed set which is the greedy solution for the robust model. So how does it perform under an independent cascade setting? Versus, how, the SICG is, the greedy solution for independent cascade. So of course that is expected to be better. So how does it perform in comparison to that? So if you look at the misspecification ratio here for S score G, the values are like 98.8, 92. So these are different settings of the probabilities. And whereas for the independent cascade, it's slightly lesser. So again, the same thing, misspecification ratio for the independent cascade is, how does it perform when used in an adversarial setting. So in all these cases, we find that the the robust set is doing better. And a feature that we see from observing the seed set is that the robust seed set seems to be picking the high degree nodes. So for example, this one. So in the Wikivote data, the max degree node was 1167. So that's of this seed set, but that was not picked for the independent cascade. And more generally, we see this reflect, like you can see this through this histogram. This is for the PollBlog's data set. Okay, so you can see this difference in the independent cascade. It stops at the seed set degrees stop at 140, but here you have some more nodes in this span. Okay. So that's a feature we see of the robust model. Now again, further on the model misspecification, there's this plot like how across probabilities, like if you change the values of the probabilities, how does the model misspecification, what do we observe? So So if you look at this plot for the pole blocks data, if you look at the orange and the blue, right? So these two. So this is corresponding to the robust seed set. So you expected it to perform like the blue curve because that is how it performs under an adversarial setup. But actually, if indeed it's the independent cascade model that's working out, what you'll get is the orange curve, orange or yellow curve. Okay. Now, on the other hand, if you look at the SICG, so that is the green and the red. So the red and the green. Yeah. So what you would have expected was the red curve because you expected an independent cascade. But if an adversary acts, what you're going to get is the green curve. Okay, so you're affected much more if you use an independent cascade towards the worse direction. Okay, so this is intuitive, but we also just see this in the data sets as well. Okay, now a final result is on the risk aversion. It's just to analyze the performance and for different values of alpha, the probability levels. For each level, there is a particular seed set which is best from the greedy selection. Now, this seed set may not be good for other values of alpha. For example, if you take this blue one as 0.01g, so that is the alpha equal to 0.01 setting. So for a small value, it is very good. But as you go away from alpha, if you plug it into a different setup of the C bar, the performance diminishes. And for example, at 0.2, if you see, the best value is the orange one, so somewhere here, but the blue one is at somewhere at this point. Okay. But one thing is the 0.01 seed set seems to be getting at least 85% of the highest in each group. So at least it's not doing too bad in terms of the risk. Okay. So this kind of brings me to the end of this talk. So what we have is a to all possible dependencies among the edge activations, and we saw that there are some computational advantages, and we did an analysis of the seed sets. Now, some of the open questions here are, an adaptive setting. So what if I don't know all the probabilities at one hand? Sometimes you learn things over time. You learn the edge activation probability step by step. You see some behavior, you're able to learn it better. Now, under that setting, what can you do? Is there a robust model that you can build? And this is something that we have just started thinking about, and some of these ideas from MDPs seems to be you know uh, fitting into that kind of a framework. These tools seem to be useful there. So this is something that we are thinking of. And also in the context of robustness, there are different families of distributions that people use. So here I showed you one particular family, which is the set of all joint distributions consistent with the marginals. Now, there are many other ambiguity sets. So one is the Wasserstein distance-based ambiguity set, where you have samples of the uncertain quantity, you construct an empirical distribution, and then look at all distributions within some radius around the empirical. So of late, there's been a lot of work on using Wasserstein distance-based sets in the context of learning. So all these problems are still open. And there's a lot of potential for these kind of models. So I hope I've enjoyed giving this talk. So I'm open now for questions.
Thank you, Divya. So if you have any questions, you can post it on the chat box. Any questions? Maybe is there a possibility to unmute and ask? Okay. So I have one simple question. That okay, now this the variants of these problems that incorporate the risk is right, like it became very common, like various in even in sequential decision making and all this stuff.
Right.
Obviously, so there is some attraction towards using this CVAR probably because of it has a very nice properties and all those things. But when it comes to this influence maximization, like any other risk measures will be useful. Like for example, simple thing like even like value at risk or or maybe or is it that just because of some nice mathematical properties of CVAR, or maybe CVAR is the intuitively conceptually best for this kind of problem? Can you comment on that?
Yeah, so actually the value at risk, that metric, even for a fixed distribution, I mean, that is hard to compute.
Yes, yes, yeah.
Right. So the CVAR has some nice properties that way, because you can compute it for a fixed distribution in terms of a convex problem. So that's kind of the reason why CVAR, kind of is more popular in that sense. I mean, it's primarily because of the computational aspects that it offers, whereas that is kind of lost with value at risk. Um,
So the other question is, okay, I don't see any question. The other question is that see when you incorporate risk into in your analysis, you might be operating slightly suboptimal, right? So
yes.
can we measure that?
Yeah, so of course, there is a lot of conservativeness that gets introduced because it's a worst case model, and also you're looking at a bad region,
Okay.
right? So, yeah, that is something which is actually there in these models because you're anticipating really the bad thing to happen. Whether it can be measured, so one thing is perhaps these price of correlations kind of ideas you can try to see, not exactly in terms of conservativeness, but with respect to other models like independent cascade, or if you have any other distributions. Now, one thing you can also do is you can take a combination of models, a mixture of different kind of models. So in your objective, you can have some weightage for the worst case model and some weightage for the independent cascade. But of course, you lose out on some properties like the computational properties. But if you do that, I mean, that can help to reduce some bit of conservativeness because it's a bad region and you're again taking a worse distribution and things like that.
Huh.
So the,
Wow. I think we are all. Thank you, Divya, for wonderful talk.